Hello and welcome. Today, we will take a deep dive into the control and communication systems, the eyes, ears, and brain of unmanned aerial vehicles. This training is not just about pressing buttons on a controller. You will learn the physical behavior of signals, the mystery of electromagnetic waves, and why legal boundaries are crucial. Why is this training important? When flying a drone, you are actually orchestrating an invisible dance. The signals from your controller transform into radio waves through the movement of electrons in the antenna. These waves travel kilometers through the air and reach your drone's brain, the Pixhawk. But what happens if noise interferes with these signals? Or if you fly on the wrong frequency and violate regulations? This training will not just answer, "How do I fly?" but rather, "How do I fly safely, efficiently, and legally?" What will we cover today? Physics of signals. How do electromagnetic waves carry commands to your drone? Control systems. Why do SBUS and PPM protocols have different latencies? Interference and legal boundaries. How do you keep your signal clean? Which frequencies are legal? For example, SBUS is more stable than PPM because digital modulation is more resistant to electromagnetic noise. We will break this down in detail. Now, let's discover how the tiny signals from your drone controller embark on a massive electromagnetic journey. 1. Electromagnetic spectrum, the address of drone signals. All radio waves are part of the electromagnetic spectrum. Drones typically operate on 2.4 GHz or 915 MHz frequencies. 2.4 GHz, higher data rate, but shorter range. 915 MHz, longer range, but lower data rate. Wavelength-frequency relationship. For example, at 2.4 GHz, the wavelength is about 12.5 centimeters. This directly affects antenna size and signal propagation. 2. How are signals generated? When you press a button on your controller, electrons move along the antenna. This movement creates electromagnetic waves. Example: when you move the throttle stick, electrons accelerate, changing the signal frequency. 3-point signal. Propagation. Invisible obstacles. Free space. Loss. Signal weakens as distance increases. Example: a 2.4 GHz signal loses about 100 decibels over 1 kilometer. Multipath propagation. Signals reflect off buildings or trees before reaching the receiver. This can either boost or distort the signal. Interference. Wi-Fi, Bluetooth, or other drone signals can disrupt your connection. Now, let's discover how your controller's electronic dance is interpreted by your drone. Modulation and protocols. First, we need to understand modulation, the language of signals. When you move the throttle on your controller, you're actually generating a number, something like 1,500 microseconds. This number is then embedded into a carrier wave and transmitted. This process is called modulation. Your drone deciphers this wave, demodulates it, and understands the throttle command. But why do we have different types of modulation? Because some signals fade into noise, while others shout, "I'm here." Now, let's talk about how these signals reach the drone. PPM and SBUS. First, PPM, our old companion. PPM sends all channels sequentially over a single wire. First channel, then second, then third. But here's the problem. PPM is a bit slow, and it's easily affected by noise. What about SBUS? Now, that's the next generation protocol. SBUS transmits all channels as digital packets, plus it includes a CRC code for error correction. And the best part? It can send 16 channels in just 3 milliseconds. That means SBUS is faster and more reliable. So, this is how your controller's electronic dance is understood by your drone. There is a constant flow of numbers between the controller and the receiver transmits these numbers to the flight controller. This flow happens through channels, and each channel carries independent numbers from the controller to the receiver. The total number of channels depends on the features of our receiver and transmitter. However, we need a minimum of 5 channels for flight. We teach our flight controller the minimum and maximum values that can come from each channel. This process is called radio calibration. Our flight controller interprets the incoming values within this range and executes the commands we give. Let me show you how it works with a video. On the left, you can see the controller and the percentage value of the numbers sent from each channel below it, while on the right, you can see the values read simultaneously by the flight card. For example, in the throttle channel, which we use to determine power, a value of 1091 is read when it's at the bottom. When it's at the top, a value of 1924 is read. This means that if the controller sends a value of 1924 on that channel, the power board will provide full power to the motors, and if the value drops to 1091, the motors will stop. Now let's adapt the concept of channels to our flight system. We determine the front of the drone during the setup phase. I am now marking the front with an arrow. I mentioned that 5 main channels are used in flight. The first 4 are for directing the drone. The 5th is used for mode selection. The first channel, known as the roll channel, is the one that allows the drone to move right or left. The second channel is the pitch channel, which allows the drone to move forward or backward. The third channel is the throttle, which tells the flight controller how much power to apply. It's also the only channel on the controller that stays in the position where you leave it. The fourth channel is the yaw channel, which makes the drone rotate around its own axis. Now that we've discussed the channels, we can move on to the flight modes. The recommended mode usage sequence on the ArduPilot's official site is as shown on the screen. It even suggests that you should move to the next mode only after you can comfortably fly in the current one. However, when you look at the explanations for the stabilize mode, it mentions that for beginners, flying in altitude hold or loiter modes might be safer and result in fewer crashes because there are fewer parameters to control. Now, let's first examine the features of these modes and try to understand why they say this. Initially, I'll explain the most basic 3 modes by comparing them in terms of 4 flight channels. In stabilize mode, the motors will spin as fast as the power you apply. The flight controller will directly transmit your command to the motors without evaluating it. This leaves altitude control entirely to the pilot. During flight, if you reduce the power to 0, you can stop the motors. Of course, the setting you see on the screen should be 0. Otherwise, the drone's propellers won't stop after being armed. Looking at the roll and pitch channels, the drone will move forward, backward, right, or left, based on your command. When you release the control stick, it will return to balance. However, it will continue on its path with the speed it has gained. Additionally, it can be affected by external factors like wind and may even drift. The same rule applies to all 3 modes regarding rotation on its own axis, i.e., the yaw channel. The drone will stop at the angle you leave it. Now, switch to altitude hold mode. In this mode, the barometer helps by detecting the height through pressure. The usage is as follows. When the throttle stick is in the middle, or more precisely in the 40 to 60% range, the drone will tend to maintain its current altitude. Above 60%, it will take off or start ascending if it's already flying. When you lower the throttle, it will start to descend or land. The pitch and roll channels work the same as in stabilize mode. Now let's look at loiter mode. In loiter mode, the throttle channel works the same as in altitude hold. This time, however, the GPS module is activated. When the roll and pitch channels are centered, the drone will start to hold its position. Even if it's pushed by wind or by hand, it will continue to maintain its position. Another thing to remember is that movements in this mode are very slow. This is because it's an important mode used especially for video recordings. Now, regarding the mode in which the first flight test will be conducted, I can say that stabilize is really difficult for a first attempt. You can see the reasons on the screen. Loiter, on the other hand, is an extremely easy mode. It feels like you control almost no parameters. With altitude hold, the risk of falling is significantly reduced because height control is managed by the board. In this video, I will try to explain fail-safe systems to you. In its simplest form, fail-safe systems are those that activate to ensure the safety of the drone when an error occurs. There are many different fail-safe settings in ArduPilot boards, each with its own independent configurations. The most commonly used ones are GCS failsafe, which activates when the connection with the ground control station is lost, battery failsafe, which activates when the battery voltage drops below a certain level, and GPS failsafe, which activates when there's an issue with the GPS connection during a GPS-linked flight. However, this video is not about those. In this video, I will talk about the settings for throttle failsafe, which activates when the connection with the remote control is lost. Now, for this, we first enter the Mission Planner interface. We establish our connection with the drone. Right after that, we go to Initial Setup. From there, we enter Mandatory Hardware. Then we click on the Failsafe tab. In the window that appears, we receive a warning that the drone's propellers should not be attached while making these settings. However, since we are already connected via USB and the drone battery is not attached, there's no need for such a procedure. We click OK to bypass this screen. Now, we will also need the remote control to make these settings. For this, I am displaying the remote control image in the bottom right corner of the screen. Now let's move on to the settings. First, we turn on the controller. While the controller is running, we see that the power channel, which is channel 3, sends a minimum value of 1091 and a maximum value of 1926. Now, what's important here is what happens when we turn off the controller, meaning when the connection is lost. Yes. As you can see on the screen, the disconnection ensures that the last value continues in the same way. I set the power channel to minimum and turn it on. After the antenna connection is established, it returns to normal operation. Now, to set the throttle failsafe, when we turn off the remote, the receiver needs to detect this disconnection and send a value below 191. So, what is this value? For this, you can see the failsafe PWM value in the radio failsafe section on the screen. This number means that if a value below 980 comes from channel 3, the flight controller will activate the fail-safe mode and switch to the preset mode. Now, let's first set up the fail-safe on the transmitter. For this, we go to the controller. We pull the trim adjustment, which we call fine-tuning, all the way down for the throttle stick. When we do this, we see that the value of channel 3 drops to 941. With this adjustment, we see that the minimum and maximum values sent from the controller drop by approximately 200 units. The current minimum value it sends is enough to activate failsafe. After ensuring this, we go into the settings of the remote. From there, we enter the failsafe section. Then, we switch the third channel, which is the throttle channel, from normal to failsafe mode and activate it with a 3% value, which is the value it is currently sending. The adjustment we'll make on the remote is this much. Then, we return the trim setting on the remote to its original value. And that's it. Now let's see if our settings are working properly. First, I set it to any value while the remote is on. Then, turn off the remote. After turning off the remote, you will see that channel number 3 drops to a value of 941. So, we activated failsafe. Now let's turn the controller back on. After the connection is established, we see that channel number 3 starts working normally. It sends a minimum of 1091. When we turn it off at the minimum, it drops back to 900 values. Now, let's finally see what we can do when failsafe is activated. First, there's always the option to activate the return to launch mode. Second, if you're flying in auto mode, there's the option to continue flying in auto mode. Third, there's the option to always activate the land mode, which means landing in its current location. This choice is very important. What should we pay attention to here? If we're using the controller from a fixed location, meaning we're stationary and the drone is flying around us, then having it return to the launch point where it took off is the most logical. One of the biggest mistakes made here is taking off from the shore when we are going to fly over the sea and starting the flight over the water. If the land mode is selected in this situation, the moment the controller connection is lost for any reason, the drone will automatically start descending towards the sea. There are many examples of this. I always choose the option to activate return to launch mode. Then I disconnect and close the connection. Now, we are ready for flight. Initially, as in other flights, I lift the drone in loiter mode. I take it far away. After bringing it to a certain point, I turn off the controller. We see on the screen that it has entered fail-safe mode, and there is a message indicating no RC receiver connection. As a result, the fail-safe was successfully activated and switched to RTL mode. It will return and complete its landing this way. Before ending the video, I also want to mention the use of GPS. If you are flying in a mode that does not require GPS before the fail-safe is activated, or if your GPS module is not working, the flight controller will switch to land mode after the fail-safe is activated. It will not be able to switch to return to launch mode. Lastly, I should mention that turning off the controller during flight is not a good idea. Therefore, I do not recommend trying this. I made sure to film this video in a safe location and stayed by the controller to ensure safety. Here's a fact. After making this adjustment, I think it's better to test it without actually needing it to see if it works. Thank you for watching. I hope it was helpful. I wish everyone crash-free flights.